All right, my friends, this is going to be a first video of two where we talk about ellipses. In this part one, we're going to show the derivation of the equation of an ellipse. And then in part two, we'll actually apply it to examples that'll be similar to what you'd see in your problem set and on any tests. So before we get going today, you're going to need to gather some materials. You'll need a little bit of tape, just 2 pieces of tape. You'll need a rubber band that you have cut so that it can be just kind of a one piece here. You'll need a straight edge. This could be a protractor or it could be an ID card or something. Doesn't have to be a protractor. And then it would be nice to have, of course, a pencil. That goes without mentioning. But then also maybe a couple of pens of color to kind of highlight important pieces as we go. Some of the diagram that we'll be drawing can get kind of cluttered in the end, and it's nice to have some color to show that certain things happened at certain times. So, so also a comment before we get going. In a lot of pre-calculus classes, they probably don't go over the derivation of the equation of an ellipse. It's a bit grungy. It's not really basically what we're going to do today is for mathematically mature audiences only. And since we are an accelerated pre-calculus class, that's us. And a lot of accelerated pre-calculus students wonder, why do you go through the derivation if a lot of classes don't? And my answer to that is students that go through the derivation have a better understanding of the concept. And you'll find that if you were to compare your experience maybe with another class that didn't go through the derivation, students in another class would ask a lot of questions over and over and over again about what the different pieces of the equations are for. But a student who's seen the derivation feels the truth in a totally different way, and you'll experience less confusion in the long run. So it's just kind of a worthwhile investment. So with that said, let's get going. The first thing I'd like to do is a fun little activity that should help you to really get an idea as to what an ellipse really is, and when we write the definition, it should help you to really feel like you understand what it's saying. So go ahead and take a straight edge, and we're going to draw first we're going to draw an XY plane. You can follow my lead for size and spacing. You notice, for example, I have quite a bit of room up above here. Okay, so all right, once you have your XY plane drawn and ready, next take your cut rubber band here, and let's see, just some explanations before we get the tape out. We are going to tack the 2 ends of the rubber band down on the x-axis, and we want to do this in a certain way. So when we tack it down, you, number one, want to make sure that you have a little bit of what I would call play in the rubber band. So that means that it's free, kind of loose a little bit. Now, so for example, you don't want to tack it down like that where the rubber band can't come free. And then you also don't want to tack the rubber band too close to each other either. At the same time, whatever distance from the origin on your XY plane, whatever that distance is where you tack it down on the right side, you want that same distance to be matched on the left side. So let's see, I'm gonna probably have mine be about like that. Okay, so take 1 piece of tape, and let's say I tack it down here. Okay, so this place right here where the rubber band becomes free, I'll put a dot underneath it and then kind of on top of it as well. This place right here where your rubber band becomes free, this is going to become a focus of your parabola. And so you need the distance, I'll just kind of mark it off here. You need the distance from what will be the center of your parabola, and we're going to try to make the origin be the center here. You need that distance to be the same on the other side. Okay, so I'm going to just put enough underneath the tape so that it won't slip out. Okay, and then we'll tape it down. So trying to make it so the rubber band becomes free at that place, right there. And this is not a perfect science, as you can see, but we try. So this point right here, where the rubber band becomes free from the tape, this is going to be another focus of your parabola. So let's just label like this point right here is a focus, and then this point right here is a focus. So we'll find that an ellipse has two foci. A comment on that word. Some people say foci, some people say foci. It's all good. All right. So next, what I'd like for you to do, once you have, again, these are equidistant, so the distance from the center out to each focus is the same. You've got it tacked down on the x-axis, and then hopefully there you've got some play in the rubber band, so some room. Okay, the next thing I'd like for you to do is take your pencil, I repeat, pencil, and kind of pull the rubber band taut. Fun situation, rubber bands are stretchy, and that's the absolute worst thing for us to do with this rubber band. So you're gonna try to pull it so that it's taut, but you're not overextending the rubber band. You're not pulling hard on it. You're just pulling it so that like there's no slack in the rubber band. Just there you go, just like that. Okay, so now what you're gonna do is you're just gonna like drag your pencil lightly and just kind of follow the path that the rubber band will let you take as you go around. And then you can switch your pencil to the bottom side. Like so, and go ahead and go over it quite a bit. And while this is not, perfect activity, I'm hoping that you can see that the path that we're creating here is elliptical. There we go. Okay. And then if yours looks super scrubby, mine looks kind of scrubby, you could always kind of go over it with a Sharpie or something to kind of make it look a little bit sharper. I'm just going to go ahead and leave mine like this. So after this activity, I think it would make sense to probably think about, well, what is the definition? And so what we're going to do is talk about, what is so special about a point that's on the ellipse? What's the relationship between, x and y coordinates that makes a point be on an ellipse as opposed to outside it or inside it? So let's look at the definition. An ellipse is the collection of all points in a plane such that. Okay, and now let's think about what was it that the rubber band helped us accomplish? What does this point that's on the ellipse have in common with all the other points that are on this ellipse? Well, since we weren't supposed to stretch the rubber band, I claim that what the rubber band was making sure of was that this distance from the point on the ellipse and this distance from the point that's on the ellipse and the focus, that they always added up to the same thing. So even though one distance was shrinking and the other distance was increasing, the sum would always be the same thing because we weren't supposed to stretch the rubber band. So an ellipse is the collection of all points in a plane such that the sum of the distances between any point on the ellipse and two fixed points and so these would be your fixed points right here, and they are called foci. I'll underline that since we just defined it. Is always the same constant value. Here we go. And when we get to the derivation of the equation of an ellipse, it's going to be very much based on this definition. Okay, so let's talk about, we're going to have some important things to point out, but first let's talk about kind of the anatomy of an ellipse. Let's see, first of all, an ellipse will have two axes of symmetry. You can see it'll have a longer one and then a shorter one. They would call the longer axis the major axis, and then they would call the shorter one the minor axis. This point right here that is as far away from the center as you can get, this would be considered a vertex. This point over here is another vertex. The points on the minor axis that are as far away from the center as you can get, these are also vertices. Some people would also refer to them as co-vertices. So let's see, I think I'm just going to put the word co in parentheses. So this is a co-vertex, and then this one down here could be called a co-vertex as well. It's not wrong to just call them, vertex or a vertex either. Okay, so next, a couple of values to represent lengths. We will say that in this case, the distance from the center to this vertex right here, we're going to call that distance all the way from here out to the vertex. We're going to call that A. And then the distance from the center of your ellipse all the way up to a covertex, we're going to call that B. And then, very important, the distance from the center to one of the foci, we're going to call that C. So go ahead and get those labeled on your picture. And then let's make a collection of important facts that will really help us in the derivation. They'll also help you with your homework when you get there. So the first thing that you're going to want to remember is what C means. So we just referred to it. So C is the distance between what two things? From the center of your ellipse to each focus. Okay. Probably technically I should put absolute value marks on that C because sometimes C is negative, but I'm not going to worry too much about it, to be honest with you. Okay, fact number 2, we're going to need to talk about the length of the rubber band. So think about, I'll give you a couple seconds to think about what do you think the length of this rubber band is. And to be clear, I'm not talking about the whole thing. Like I want to disclude these little nubbins that are underneath the tape. So I'm referring to the part of the rubber band that's free. So I guess I should say length of the free part of the rubber band. Yeah. So, and if you're not sure, one thing I could do to kind of help you see it is I could pull the rubber band over here to the part where we were drawing that vertex right there, and maybe look at it now and think about, what do you think the length of the free part of the rubber band is? And your answer would be in terms of either A, B, or C. It can be argued that the length of the rubber band is 2A. And how come? So you can see that the free part starts here. It goes almost the entire length of the major axis, except for this little piece right here, this distance. But that distance would be this kind of little double overlap piece. So if I was able to cut this little extra piece out and move it over here, then I'd have exactly the length of the major axis. So I'm hoping that you're comfortable at this point with us saying that the length of the rubber band is 2A. And then another important note is that this 2A value is also the length of the major axis. There we go. Okay. Let's see, fact number 3, and we're really just getting set up for the derivation at this time, but this stuff is helpful for doing just this knowledge is helpful for doing the whole problem set also. But fact number 3, let's talk about what's called the Pythagorean identity for ellipses. Okay, so what we're going to do is just use the good old-fashioned Pythagorean theorem, which, remember, is just a way to compare, it's a relationship, that is, between side lengths of a right triangle. And to help you see the Pythagorean identity, I think what I'll do is grab this rubber band, and I'm going to hold it right there where we were drawing, whoops, sorry, wiggled you there a little bit. Where we're drawing the co-vertex right there. And look for a right triangle. You could probably see 2, but I'm going to have you focus on this one right here. And think about, what would the Pythagorean theorem say about that triangle? And so hopefully you can see the right angle right here formed between the x and y axes. And then what's the length of this leg? It would be C. The length of this leg would be B. And then what would the length of the hypotenuse be? Well, what did we just say the length of the rubber band was? 2A. And then if I hold it right up here at the top, I hope you can see I've got myself an isosceles triangle. And so this half of the rubber band is the same length as this half of the rubber band. So if the whole thing is 2A, then what's the length of this hypotenuse of this right triangle? I hope you're okay with it being A. So I'm just going to go ahead and draw that triangle in. So here's that hypotenuse that I'm referring to. It goes from the co-vertex down to that focus. And the length of it is A, half of the rubber band. And just to be clear, we are focusing on this right triangle right here to get this relationship. Okay, so, and here's your right angle, boom. Okay, so what would your Pythagorean identity be? What would the Pythagorean theorem say about that right triangle? It would say that a squared, which is the hypotenuse, would equal b squared plus c squared. And then typically we would isolate c squared for our purposes, because typically we're finding the location of the foci of the ellipse. And so if you isolate c squared, you just subtract b squared over, and so c squared would be equal to a squared minus b squared. And if you look at the Pythagorean identity for ellipses, it kind of looks like somebody doesn't understand basic geometry, like they're just screwing up the Pythagorean theorem. But they aren't, because we really used a legitimate application of the Pythagorean theorem. It just so happens that for us, the a value is larger than the c value. So this is how it works out. So I'm going to put a little star there because that's going to be worth memorizing. Also, the fact that the length of your major axis is 2a is worth memorizing. And also that c is the distance from the center to each focus. Very much worth memorizing. Okay, and then we're going to go from here to getting started on the derivation. I do think I'm going to give you a little snapshot of what our derivation is going to look like. Not to freak you out, but just to kind of give you a heads up as to what this will look like. It's a little smudgy, so forgive me for that. But this is kind of what your derivation will look like. You can see quite a bit of algebra grunginess. You are going to understand every lick of it as we go through. But I really want to draw your eye to how cute it looks when you're all done. So this is definitely it gets worse before it gets better situation, but it's gonna look super cute when it's all done. And thank goodness somebody cleaned it up and didn't tell us to memorize any of the kind of mid steps here, because that would have been really hard to apply. Okay, so let's get started on that. Okay, so first of all, let's make sure you're okay with the whole idea of what our goal is and then how we're going to get started. So first, our goal is to show that the equation of an ellipse, and in this case, we're going to keep our derivation as simple as possible. So we're going to say centered at 0, 0. I figure if we derive the one that's centered at the origin and we're good at shifting things, then it should be no big deal. Okay, so we're wanting to show that that equation is going to be this cute. X squared over a squared plus y squared over b squared equals 1, the loneliest number. Okay, and so to get started on it, we're going to start with, according to the definition of an ellipse, if you reread it, what makes a point be on an ellipse? Well, if you think about what did the rubber band make sure of? Like, for example, this point XY right here. What did it make sure of? It made sure that this distance plus this distance would always be the same thing, whether you're here or here or here. You add up those two distances and you always get the length of the rubber band. And so I think what I'll do is we're going to focus on this point right here, XY, and I'm going to draw in where the rubber band was. So it went from the focus to that point. I'll call that distance 1. And then the rubber band also went from this focus to that point. I'll label that as distance 2. So according to the definition of an ellipse, distance 1 plus distance 2 always needed to be the length of the rubber band, which was the same as the length of the major axis. So that would equal 2a. So from here, we're going to use the distance formula twice. Before we do that, though, we're going to need to label the coordinates of all the points in interest. So this one's already labeled x, y, and the whole thing is about showing what's the relationship between this x and y that makes you be on as opposed to off the ellipse. But we're going to need to label the coordinates of this focus right here and this focus right here. So what would the coordinates be of this focus right here? Well, how far is it from the origin? You went to the right, C, and up 0. So the coordinates of this focus would be C0. And what are the coordinates of this focus right here? Well, you went to the left, C, and up 0. So I claim the coordinates would be negative c0, there. So let's use the distance formula and get an expression for this distance right here. So distance 1 would be the square root of x minus negative c, or x plus c squared, plus y minus 0 squared. And then we're going to add distance 2. Distance 2 would be the distance from this point to the focus. So what would that be? X minus c squared plus y minus 0 squared. And the whole thing should add up to 2a. Okay. Moving from here, actually, let me get some of that paper back. Okay. All right, my friends. Moving from here, really, it's all about a whole bunch of algebra simplification just to make this look this cute up here at the top. So let's get going on that. Notice if you look at what we want it to look like and what we have, we definitely want some things to go away. So what are some things that we have here that we don't want to have in the end product? We don't want to have square roots. First of all, I know you were thinking it. We got to get them to go away. And then also notice that the end product doesn't have any c values in it. So we're hoping that somewhere along the process we can get those c values to go away. And so keep those two things in mind. So I'm going to make goal number 1 be to make the square roots go away, and then goal number 2 is going to be to make the c values go away. So let's talk about getting rid of those square roots. Can I just square both sides of this equation? Yes. However, I claim that if you square the left side of the equation, because of the FOIL process that you'd have to use, you would end up with a pretty grungy middle term. That would be 2 of this times this, and it would still have a big square root in it. So you'd kind of go from bad to worse. So with that said, you're going to see me move one of the square root expressions over to the other side and then square both sides. It's just a little bit better, in my opinion, than squaring now. So when we're at it, I'm also going to simplify the square root here as the square root of x plus c squared. And then y minus 0 is just y, so y squared. And then, as I mentioned before, I'm going to subtract that square root over to the other side. So I'd have 2a minus x minus c squared plus, and y minus 0 squared is just y squared. Okay? Now, as I mentioned before, I'm going to square both sides. Okay, and the left side, yay, the square root goes away, so that's great. So on the left side, I would have x plus c squared plus y squared. And then on the right side, we'd have to use the FOIL process to square it. So you'd end up with the first term squared, which would be 4a squared. You'd end up with the first and the last term multiplied together, but then doubled. So you'd have minus 4a times the square root of x minus c squared plus y squared, and then you'd end up with the last term squared, so the square root would vanish. So you'd have there we go. Did I mention that this is going to get worse before it gets better? Here we are. Okay, so now let's look at this situation. Look for something that could simplify. And I hope you notice that on the left side of the equal sign, you have a y squared term, and on the right side, you also have a y squared term, so you could subtract them out and they would vanish. So I'm just going to save myself some work and just go ahead and let those kind of subtract out. And then in the spirit of getting rid of this final square root, I'm going to try to isolate the term that has a square root in it. And so you're going to see, oh, you know what, actually, before we do that, let's expand x plus c and x minus c squared. So, because we'll have more stuff that's going to go away. I think this is a good time to do that. Okay, so x plus c squared would be this expression. And then x minus c squared would be x squared minus 2cx plus c squared. Okay. So thanks to that, what are some things that you could subtract off of both sides and they would vanish? These c squareds you could subtract off from both sides, and then the x squared, it looks like, also. Boom, there we go. That was fun. And then notice the 2cx and negative 2cx, they're at least like terms. So if you add 2cx over, you could at least combine them together. And then, as I mentioned before, I do want to isolate the expression that has this square root in it. So I'm also going to subtract the 4a squared over. Okay, what do I now have? I have 4cx minus 4a squared. And on the right side, I have negative 4a times the square root of x minus c squared plus y squared. Okay. There's so many ways that you can do this problem. The next thing I like to do is divide both sides by 4 to get all the 4's to cancel out. So I would just have cx minus a squared equals negative a times the square root expression as is. Okay, now that we've got that, I think this is a great time to go ahead and square both sides. Okay, if I do, what would I then have? Can I just tell you that I really miss having everybody in class to fix all my mistakes? This is not my first time doing this video. All right, let's square the right side. We'd have a squared times the quantity x minus c squared plus y squared. There we go. All right, let's see. Oh, trying to get this thing to clean up. On the right side, it's time to expand the x minus c squared. And then on the left side, we've got that, okay? We're gonna distribute the a squared in. Okay, there we have it. Okay, so let's look at this. Is there anything that will vanish if we were to, I don't know, add it to both sides? It would go away. Looks to me like this negative 2a squared cx, we could add it to both sides and make it go away. Excuse me. Okay. Anything else, or is that it? Right? There's no, okay. All right, that's it. So this is a place where people oftentimes lose momentum, understandably so. But we've accomplished goal number 1 of making the square roots go away. So let's remember, what was goal number 2? If we're gonna make it look like this, notice that this doesn't have any c terms at all. But we've got lots of c terms here. And not only that, but we have c terms squared. And so I'm hoping that kind of makes you want to reach for this little gem, Pythagorean identity, where c squared could be swapped out for a squared minus b squared. So that's what you're gonna see me do. Anywhere that there's a c squared, where do we have them? Just 2 places. We're gonna swap it out for a squared minus b squared. So there we go. All right, my friends. Now we'll just follow our distribution property nose here. So we'd have a squared x squared minus b squared x squared plus a to the 4th. On the right side, we'll have a squared x squared plus a to the 4th. minus a squared b squared, and then plus a squared y squared, like so. All right, my friends, let's look for things that could vanish. That's my favorite thing in this process, is getting things to vanish. The a to the fourths do vanish. Oh yay, and the a squared, looks like the a squared x squared is a goner. And I think that's it as far as things that we could subtract out and have go away. Okay, so now if you look at what's left and look at what we want it to look like, notice that our goal up here has the x and y terms on the same side, and then it has like the I'm just going to call that like a non-x and non-y term. In that case, I would really like to take this x term and move it to the right side. And then this doesn't have x or y in it, so I like the idea of adding it over to the other side. And you do not need to show this step quite like that, unless you want to. So these would then vanish, and what would I have on the left side? And then what would I have on the right side? These would be gone. I would have a squared y squared. Actually, let me write it the other way. Let's write the other one first. I would have b squared x squared plus a squared y squared. All right, my friends, so look at where I'm at. I've got x squared and y squared on the right side. I have the non-xy term on the left side, and look at where I'm wanting to go. And think about what's the last thing we would need to do to get it to look like that. And you could do it in one step. I'm running out of room, so I'm going to go ahead and show it in one step. You could divide both sides by a squared b squared to get that 1 over there. And then I'm going to go ahead and show the division distributed on the right side to make it a little bit easier to see. So what would I then have on the left side? I'd have the loneliest number of 1. On the right side, these b squareds cancel. I'd be left with x squared over a squared. And then on the right side, the last term here, the a squareds cancel, and you're left with y squared over b squared. And we did it. All right, my friends, that is how super cute the equation looks. And then in the next video, we'll talk about how easy it's going to be to use it. And then we'll also talk about how to find the foci of an ellipse. Hope this is helpful to you. Take care, everybody.